Hello everyone, this is a tutorial on the theoretical foundations of reinforcement learning that I'm working on with Alec Agarwal and Akshay Krishnamurthy. This is for Fox 2020. At the bottom of the slide there's a URL to a website which has some additional pointers and information. The goal of this tutorial is providing a reference to key advances in reinforcement learning theory. We want to enable people to understand the substantial changes that have occurred over the last half decade or so in our understanding of what's possible in reinforcement learning and how well reinforcement learning can be solved. Another key goal here is describing unresolved questions in reinforcement learning theory, because I guess we're secretly hoping that very smart people will come and solve these problems for us. I'm going to start with the basics of reinforcement learning, things that we knew a half decade or more ago. And then Akshay is going to go through the information theory of reinforcement learning. What is possible statistically and how can we do that? And then Alec Agarwal will be covering the optimization approach to reinforcement learning. How do we use gradients in order to effectively solve reinforcement learning? Then I'm going to close with the latent state approach to reinforcement learning. The idea there is that you discover latent unknown state and then use that to effectively plan and solve reinforcement learning. In the general setting of reinforcement learning, you have the world and then you have some agent which is trying to cope with this world. The world will send observations to the agent. The agent will then use a policy which tries to choose amongst different possible actions dependent upon the observation that it made. It chooses some particular action. That action is taken in the world, and the world may respond with another observation. The agent then considers this observation with its policy, choosing amongst several different actions again. It chooses some action, and then it observes a reward. The goal here is maximizing the sum of rewards that the agent observes over time. So there are many variations of this. Maybe it's 100 time steps of interaction before you see a reward. Maybe it's only 1 time step before you see a reward. Maybe there's different shapes to the observation spaces, there's different choices of the action space. All of these variations are considered reinforcement learning. There are problems where an agent needs to discover how to act so as to maximize the rewards that are observed over time. Why do we care about reinforcement learning? Perhaps the most important is that this is a fundamental and natural problem. This is the kind of problem that we seek when we're trying to figure out what the foundations are, because this is about the foundations of many different kinds of learning. In nature, there are many different species which have shown reinforcement learning all the way down to worm scale. You can train some worms to seek and avoid various situations. Another very practical reason to care about reinforcement learning is because a lot of problems are better understood as reinforcement learning problems. And when you frame them right as reinforcement learning problems, you discover there are additional effects that exist beyond simple supervised learning. Taking these effects into account can allow you to achieve better performance in your problem. So for example, instead of predicting click or no click for an ad or a news article that you may want to display, you can instead treat it as a recommendation problem where you're trying to choose what to display. And then because it's a decision problem where you're trying to make that decision, you want to use the reinforcement feedback about a click or not. But because it's a reinforcement learning problem, you know that you need to actually explore alternatives in order to discover the right solution. Same thing happens with dialogue systems. In dialogue systems, maybe you want to predict the intent of an individual person. After predicting that intent, you need to come up with some utterance. But if you instead think of this as a decision problem where you need to come up with the next utterance based upon your observations, then perhaps you can achieve better performance, or you can shortcut in the process of predicting the intent and then inferring from the intent what utterance to do. Same thing happens in games when you're trying to predict whether or not you should go north, east, west, or south. And in a server farm, maybe instead of predicting the queue sizes, you really want to try to assign jobs to servers so as to minimize the queue sizes overall. So all of these problems have the flavor where they're really decision problems that just happen to be partially phrasable as supervised learning. Often they were solved as supervised learning in practice. These solutions were often incomplete. And by taking into account extra aspects of the decision or reinforcement learning problem, you can achieve better performance. There's a third very natural reason to consider reinforcement learning problems, which is that many just cannot otherwise be solved very effectively. An interesting example here is Go, where DeepMind has effectively solved Go using this AlphaZero through reinforcement learning. So we didn't know how to do that with a supervised learning approach, because even the best Go players in the world are not authoritative about which action is the right action to take in various contexts. Using reinforcement learning, they were able to discover what the right action to take was in many more contexts than a human could possibly evaluate in a lifetime, allowing them to achieve a solution which is much better than humans have achieved in the game of Go. I want to give a few examples of reinforcement learning. A common one is predicting which news article is of most interest to a user. You can treat this as a reinforcement learning problem, which implies that you need to actually explore alternatives and discover what is the most interesting article at this time for this particular user. In doing this, many different companies manage to find the content which is of more interest to a user than other approaches might achieve. A very different approach is robotic hand manipulation. Can you actually manipulate the Rubik's Cube with fingers so as to solve it effectively? OpenAI demonstrated that this is in fact possible using reinforcement learning techniques, something that which had never really been done before. Another very different one is solving the game of Go. DeepMind effectively solved the game of Go using this AlphaZero algorithm, which learned from scratch, just knowing the rules of Go alone, how to achieve performance well beyond what human masters could achieve. One last common one is wellness. You'd like to be able to nudge people into healthier habits. Maybe we should all walk a little bit more, or maybe we should take breaks while we're working with a computer. If a reinforcement learning agent can learn how to nudge people, that is potentially of great value across all the population together. Let's think about reinforcement learning more precisely. In a reinforcement learning setting, you repeatedly loop through episodes. Here I'm thinking about episode as being big H in length. So you're going to have big H steps, one after the other. And in each of these steps, you're going to see some observation. So for example, if we're considering navigating through a park, our observation might be our view of the trail. And then we're going to choose some action, which could be turning left or right at the fork, or maybe going cross country. And then we're going to get some reward, which is finding the mountain peak, right? So if we get the good view, maybe we have some reward and we feel happy. The goal in reinforcement learning is to minimize the regret to a policy class. So there's some family of policies that we consider. This family of policies might be very complex. It could be dense net systems with 192 layers and millions of parameters for object recognition. Or it could be just a boosted decision tree. It's various different model classes that we're familiar with from supervised learning. Each forms a policy class, and we want to compete with whatever policy class we're using. So what does regret mean? Well, regret means that you have some best policy in your policy class that has some accumulated reward over your episodes. And then you have some action that your algorithm actually took. You want to compare these numbers, and you would like these numbers to not be very different. So you want these numbers to be, the difference of these numbers to be small. So your goal is to minimize the regret in your policy class. Once you have a setting, it's natural to consider a lower bound in the setting. And it turns out that there's a pretty difficult lower bound in this particular setting. Suppose you have two actions available, then after h different time steps, you'll have 2 to the h leaves. If only one of these leaves has a reward, it can be very difficult to discover that particular leaf. In particular, you may need to enumerate 2 to the h different episodes to discover that leaf. So enumerating 2 to the h different episodes implies that the sample complexity or the regret has an exponential dependence, which is quite difficult to overcome. This exponential is much more fundamental than other exponentials that you may have observed in other aspects of machine learning. The reason why it's so fundamental is because when you run an episode and you reach one of these leaves, you only get feedback about the policies which chose that leaf. You don't get any feedback about all the other policies. In contrast, in supervised learning, after every individual example, you get feedback about all of the possible policies. Maybe policies chose the wrong action, but you still learn that it was the wrong action. Here, you don't learn about that. And because you don't learn about that, you may require an exponential number of episodes to discover the best policy. So this observation has been made in several different ways by several different groups of people over time. Because of this observation, we're going to be forced to use something beyond the simple, straightforward statement of reinforcement learning. There's going to have to be some forms of simplicity in the world which allow us to achieve reinforcement learning. We know that it's possible in practice because people do it all the time, animals do it all the time. Many kinds of reinforcement learning are evident around us. And so the challenge is going to be discovering exactly what configuration of additional restrictions create a natural reinforcement learning problem, which gives us the leverage we need in order to solve real-world problems. Let me give you an example of the family of problems that you encounter in reinforcement learning. In some cases, it's natural to consider an episode of length big H. In other cases, people consider an episode of infinite length where they discount the future. So they care about the results t time steps into the future, gamma to the t less, where gamma is some number which is less than 1. Consider gamma to be 0.9, 0.95, 0.99. These are kinds of natural numbers people use. So I want to encourage you to think of this as not an important difference, because these two settings don't really change what you can prove in any appreciable way. Right? So in particular, you can think of a discount of gamma as terminating with a probability of 1 minus gamma and having no discount, because the expectations will end up working out this way. So given that you can think of this terminating with probability 1 minus gamma, after about 1 over 1 minus gamma time steps, an episode will probably terminate. And so you can think of gamma as having an implied horizon, or horizon as having an implied gamma. And when you look at results with one kind of horizon, you can typically translate them to the other kind of horizon with some lossage, but not too much, using this kind of simple transformation. I want to go through the key challenges which unite the different reinforcement learning settings. The first of these is credit assignment. The idea with credit assignment is that you want to know which action was taken wrong. Maybe this is a wrong turn in a park when you're trying to reach the peak of a mountain, or maybe this is the move where you lost the game. In each case, you're trying to understand which action went wrong. So that's a key challenge which occurs in reinforcement learning settings. And an example of a possible solution is dynamic programming. In dynamic programming, you have some start and some end. You start at the end, and you back up and you ask which things can easily reach the end, and you calculate the cost of reaching the end. And then you take a min over the different paths to reach the end. And then you take all the steps which are 2 away from the end. You consider different ways to reach the steps which are 1 away from the end. You take the min over those possibilities, and you keep iterating this process over and over again until you get to the start. And then you discover the shortest path. All right, so another key challenge in reinforcement learning is exploration. And exploration can be thought of as trying to gather the information you need to learn. How do you gather the right data so that you can learn effectively? I remember a few years ago there was big data was the buzzword, but I think right data is what we're looking for here. How do you gather the right data in order to learn effectively? Okay, so that's a simple version of this. An example solution for exploration is epsilon greedy. This is probably the simplest form of exploration that exists. The idea is that you have some policy, and with some probability, you're going to act according to the policy. And with some other probability, with the remainder probability, you're going to explore. You're going to try other alternatives in order to discover what is the best solution. Right? So there's a combination of exploiting for performance and exploring to discover new things. And then, okay, so why don't you explore always? Well, you also want to achieve small regret or otherwise achieve good performance. So that you run into an explore-exploit trade-off, which is very common in reinforcement learning, where the question is how much should I explore to discover how to best perform? The last key challenge in reinforcement learning is generalization. This is essentially trying to learn to act based on things that you've never before seen. We're actually very familiar with generalization from supervised learning. If you look at supervised learning, there's many forms of this. One of them is by Bandit, PAC-learning, the theory of the learnable. The goal in supervised learning is to generalize from past examples to future examples. So this is canonically done by considering unsupervised handwritten digits. You hire somebody to label these digits. The labeled digits are then fed into a supervised learning algorithm that spits out some classifier, which can take as input other unsupervised examples and give you as output predicted labels. Okay, so a key technique which has been useful in many reinforcement learning analyses and theories is this notion of a learning oracle or reduction. This comes from looking at the process of supervised learning. So in supervised learning, if you look at where people have been able to prove that you can learn efficiently, it's only for relatively simple function classes. So the neural networks people use nowadays are just deeply intractable to discuss the computational complexity of learning. Nevertheless, you would like to be able to reason about complex function classes because you want to use them in practice in real applications, right? So there's kind of a stumbling block here. Computationally, we don't know how to address complex function classes. Practically, we'd like to use them, and then theoretically, we'd like to reason about the use of them. So how do we get around that? Well, the common observation is that for many of these complex function classes, search through them does succeed, even though in the worst case, perhaps, it does not succeed. So in practice, you succeed in finding a pretty good solution for object recognition, even though this involves millions of parameters with deep nonlinearities. Okay, so that's an interesting observation. So an approach we can take is to say, look, I'm going to assume that we can solve any supervised learning or PAC-learning problem in unit time. Oh, I forgot to mention, PAC-learning here is probably approximately correct learning, which was Valiant's terminology for it. Right, so the result is quite a few algorithms at this point that can solve complex problems in practice. Voppel-Wabbit here is a online learning tool, online learning system that uses reductions systematically in its design in order to address a large number of problems with the same basic core learning algorithm. Once we have these three key challenges defined and described, we start thinking about combinations of the challenges. A natural and simple combination is just exploration plus generalization. So there's no credit assignment here to worry about. This is typically called the contextual bandit setting. In the contextual bandit setting, you're going to repeatedly see features X, make an observation X. You're going to choose an action A, and you're going to see a reward. Your goal is to minimize the regret, but now our regret is much simpler because we're just thinking about IID sequences. We're thinking about situations where your action does not influence the future observations that you'll make. In that setting, suddenly things become much simpler, they become much more tractable, and we become able to deploy systems in the world. Contextual bandits have a rich history. It starts almost a century ago with Thompson sampling. The idea of Thompson sampling is you're going to sample from the posterior of a Bayesian distribution. After the Thompson sampling, various developments in bandit-style algorithms happened for a while. And the first contextual bandit-style algorithm that I'm aware of is EXP4, which was published in 1995 by members of the Fox community. This works even in adversarial settings, which is even more robust than the setting I described with IID samples. Moving beyond that, we wanted to achieve something that was computationally efficient, because EXP4 is not. It enumerates every possible policy and keeps track of a number for every policy. So in practice, supervised learning can succeed exponentially more efficiently. And we noticed that you can, if you think of supervised learning as an oracle that you can invoke, then you can solve contextual bandits efficiently in a manner which is slightly suboptimal statistically or in terms of the regret that you achieve. This gave us a key problem. We wanted to combine the benefits of EXP4 in terms of the regret or statistical performance and the computational performance of Epic Greedy. So going forward to 2011 or 2014, we figured out how to do this. We figured out how to use a supervised learning oracle multiple times in order to achieve something that was both computationally tractable and statistically efficient at the same time. Backing up to 2010, there was a problem of web recommendation that I encountered when I was at Yahoo Research. We had our first deployments of contextual bandits in practice. And then a decade later, this has turned into a product. We actually have a product where you can go and get your own contextual bandit. You can feed it features. You can, for each individual action, you can wait for it to tell you which action to take, and then you can tell it the reward for the outcome that action achieved. And then the process, the system will try to learn online how to perform better and better and better over time so that you can do anything that a contextual bandit can do. Another facet of reinforcement learning is what I think of as tabular MDP learning. So the idea here is that we're not going to care about generalization at all. Instead, we're just going to care about credit assignment and exploration. So in that setting, people think about a tabular markup decision process. So for a tabular markup decision process, you have a set of actions available. You have a set of states. You have some initial state distribution. Then you have a transition table. This is kind of the key concept. So the transition table tells you what is the distribution over next states given the state that you're at and the action that you take. And then there's some reward distribution or reward function, which given the state that you're at and the action you take gives you a reward. All right, so if you're in an MDP, a markup decision process, how do you learn effectively? So there have been several papers, and the core idea is that you can kind of observe states and actions and next states just by exploring around inside of the MDP, even at random in the beginning. And then based upon these observations, you can build a model of the world. It'll be imperfect, but you can build an approximate transition matrix and an approximate reward function or distribution. And then using this approximate, okay, so let me tell you why you're not done. Right, so if you just do epsilon greedy exploration, it's very easy to construct MDPs where you'll essentially never reach states that you want to reach because the dynamics just don't favor that. All right, so think about a random walk up when there's a hill. You're not going to reach the top because most of your steps will end up going down the hill. And so thermodynamically, it's exponentially small probability of reaching the top of the hill. All right, so we need to fix that. And the claim is that you can fix that. If you build these imperfect models of the world, then you can plan in that imperfect model. And okay, so several things happen when you plan in that model. You're going to plan to reach somewhere that is unobserved or that maximizes your reward. There's some delicacies around exactly how that works out. But when you execute that plan, you're either going to reach somewhere unobserved, or you're going to discover that your imperfect model of the world was imperfect, and you'll improve it. Either way, you're winning, because you're developing a stronger understanding of the world, which allows you next time to plan to reach new states better. Okay, so the result that you get with these kinds of algorithms is that there's some sort of polynomial in the number of states and actions and time horizon and so forth required to find a policy which is near optimal. Okay, so let's look at the history of that. So the history here is E cubed was the first version of this, and there was RMax, which came a little bit later. E cubed had Michael Kearns involved, who's I think often published things at Fox in the past. If you look later on, we figured out something kind of cool. It's possible to succeed with a linear complexity in the number of states. And so naively, you might imagine that constructing these transition matrices requires something proportional to the number of states squared. But it turns out that linear in the number of states is possible. And then Peter Auer and others worked out how to achieve a near optimal regret, which is a great improvement on these previous algorithms. And then just recently, Qi Jin, Sebastian Bubeck, Michael Jordan, and others worked out how to achieve a near optimal regret in a model-free way, which is very efficient and simple to implement. So that's great. What you don't see here is practical deployments of the system. Why don't you see that? Well, it's essentially because of the lack of the generalization. Generalization in practice is a requirement for deployments, as far as I've observed. Okay, so let's think about the reinforcement learning problem. We have credit assignment, we have exploration, we have generalization. These are the core challenges of reinforcement learning. We have contextual bandits, which is a very practical form of reinforcement learning that is now pretty widely used. We have tabular MDP learning, which combines exploration and credit assignment. No common uses yet, but still it's a very interesting core theory. And then there's also policy improvement methods, which Alec is going to talk about in more detail. These policy improvement methods have been used to do great things. So solving Go is a pretty substantial accomplishment. But you really would like something which combines all three, right? And now, how do we actually combine all of these? That's kind of the key challenge. All right, so we're going to be, the rest of this tutorial is going to be about the policy improvement part and about combining all three of these in order to achieve solutions that address all three challenges simultaneously. Next, Akshay is going to talk about the information theory part of reinforcement learning.
In this part of the tutorial, we're going to cover some of the information theoretic results that we know and what is statistically possible and statistically not possible in reinforcement learning. To present the results, I'd like to go through some notation so that we have a way to discuss these things in a precise way. So we're always going to consider finite horizon episodic reinforcement learning problems with an episode length of capital H. And the way an episode works is that we observe a start state, which is sampled from some distribution. And then for each time step, we observe the current state, we take some action, and then we observe some scalar reward, which for normalization, we will restrict to be in the interval 0, 1. And then the environment transitions to the next state, xh plus 1, which is sampled from the transition operator t, which associates a distribution over states to every state action pair. So the picture is that we're in some state x1, and we like to think about the states as being very high dimensional, for example, images. We take an action, we transition to a new state, and so on and so forth. And in this problem, the goal is to accumulate very high rewards over the course of the episode. And we formalize this using the notions of policies and value functions. So a policy is just a decision-making rule. It's just a mapping from the state space to the action space. And the value of a policy is the reward we would get if we executed that policy for a full episode in expectation. So what we'd like to do is we'd like to find a policy that maximizes the value. And we measure the performance of a learning algorithm using two notions. So one is PAC-learning, which is very familiar to you if you have followed the supervised learning literature. And here we'd like to output a policy pi hat who has near optimal value in as few episodes as possible. And I'm going to use as notation V star to denote the optimal value. This is the value the best value you could possibly achieve, and pi star to denote the optimal policy, which is the one that achieves the optimal value. So that's one objective. The other objective is an online notion of regret, which is we're going to run our algorithm for t episodes, and we're going to measure what is the total reward the learner picks up, and compare it to what we could have gotten had we run the optimal policy for those t episodes. So these are the two types of learning goals we're considering. Now, note that when we're trying to compete with the optimal policy, we're searching over the set of all mappings from states to actions. And if we're thinking about states as being images, the search space is extremely large. So this is going to be a very, very difficult search problem, statistically. And note that also, because the search space is so unrestricted, there's actually no ability to generalize here. Because even if we knew the optimal action for one state, it would impose no constraints on what the optimal action is for any other state. So in order to bake in generalization into our formulation, we're going to restrict the search space that we look for our solutions in. And there's three ways to do this. So the first one is called policy search, where we simply just consider a restricted policy class. So someone will give you a set of policies, capital pi. They're a subset of the set of all mappings from the states to actions. And these policies might be like classifiers. So maybe multi-class linear classifiers or linear threshold functions. And you're going to search over this restricted class. Another popular way to do this is through the notion of value-based reinforcement learning. And here what we're going to do is we're going to search over a restricted set of score functions or action value functions. And these are functions that associate a real number with every state action pair. So you can think of them as scoring the quality of an action at a particular state. And these Q functions, as they're called, naturally induce policies. And we call, for any Q function, the induced policy will be called PAC-Q, which makes the decision that is the action that is scored the highest according to the Q function at a particular state. And when we're considering this sort of approach, the typical thing we're actually trying to approximate is what's called the Q star function, or the optimal action value function, which maps each state action pair to the long-term reward we could achieve if we started in state X, took action A, and then behaved optimally thereafter. And this Q star function has a very nice recursive form where it's the immediate reward plus the Q star function at the next time. And this is known as Bellman's equation. The last way we could do this, note that Q star encodes the optimal policy if we take the greedy action with respect to this Q star function. The last way that we could do this is what's called model-based reinforcement learning, where we try to approximate the dynamics in the reward function directly. And once we've done this, we can actually use planning techniques like dynamic programming in our learned model to learn the optimal policy. So these are the kinds of solution concepts that we'll consider. And for most of the talk, we'll think about value-based methods. At the very end, we'll discuss some model-based ones. So now that we have this sort of notion of generalization built in, we can restate our goal. So focusing on PAC-learning, the goal is to output a policy pi hat, whose value is about as good as the best policy in our induced policy class in as few episodes as possible. And so if we're thinking about these policy search methods, this class capital pi will be the restricted class that we're searching over. If we're thinking about value-based methods, this will be the class of induced policies induced by our set of action value functions. This is the class of induced policies. And in terms of sample complexity, what we're hoping for is sample complexity that scales polynomially with the number of actions, the time horizon, some notion of statistical complexity of the function class that we're using, and the accuracy parameter 1 over epsilon. And when I mention this statistical complexity term, I'm thinking about statistical complexity should be like log number of functions if your class is finite, or maybe D if your class is d-dimensional linear predictors. This is sort of the quantity you would get if you did supervised learning analysis. And note, in this goal, there's no explicit dependence on the cardinality of the state space, which is sort of suggesting that we are generalizing across the states. Now, so far, we've actually not precluded this exponential tree lower bound that John discussed in the first part of the tutorial. And I think it's worthwhile to go through this a little bit because it will sort of hint at what additional assumptions are required for reinforcement learning. And the point here is that reinforcement learning is very different from supervised learning. So let's consider a kind of a cheating setting where I'm going to repeat the following experiment n times. I'm going to sample a state action pair from some data distribution D, and I'm going to reveal to you a scalar y, which is the Q star function associated with that state action pair. So this is the optimal reward we could achieve if we started in state X and took action A next. And you have this data set, and the kind of the obvious thing to do is to try to predict the Q star function using your function class that you have. So you're going to solve this least squares regression problem where you try to use the state action information to predict this label y, which is the Q star value. And when you solve this least squares problem, you're going to get a function Q hat. Now, a standard supervised learning analysis will reveal that in expectation over state action pairs sampled from the distribution, the function that you learn Q hat makes predictions that are very similar to the optimal Q function Q star. So this is great. So actually supervised learning works great. It actually works in the exponential tree, no problem so far. The problem comes when we think about what is the performance of the induced policy. So remember, I have a Q hat function. The natural induced policy is the greedy one with respect to that Q hat function. And the issue is we actually cannot really say anything about the performance of this policy by hat unless we make further assumptions about the distribution D. And the reason is that if pi hat takes some action that is not supported by the distribution D, we have no idea what Q hat will predict relative to Q star. So Q hat might grossly overpredict the performance of the induced policy, and this is going to be a real problem. So the picture to keep in your head, thinking about the exponential tree, is that suppose the data distribution D is supported only on the right half of the tree. Now, the supervised learning guarantee will just say that on the right half of the tree, your predictions are accurate. But it will not say anything about what's going on the left half of the tree. And in particular, your policy pi hat is going to deviate to the left half of the tree because there's zero reward on the right half. But once it leaves the right half of the tree, we have no idea where it's going to go. And there's no reason to believe that it will go to where the coin is, where the reward is. So this is the problem. And we like to call this problem distribution shift. And what's really going on here is that the states where we evaluate the induced policy pi hat are not the states where we fit the Q function Q hat. So pi hat can sort of wander off the data distribution that we use for training. And this sort of suggests that we need some stronger notion of generalization. We need to be able to generalize outside of the distribution with which we trained our Q function. And so this is one of the core issues in reinforcement learning. And to date, I think there are basically two ways to address this. The first way is to sort of assume something about the environment itself, in that there's not that many data distributions available. And I'll show you one example of this. But somehow, if this is the case, then if you collect data from all of these data distributions, then you're good, because your pi hat cannot wander off of the support. The other way is to make assumptions about the environment and the function class in a way that the function class directly supports some notion of out of distribution generalization. And we typically call this extrapolation. And then we'll see a technique that sort of does a combination of these two things. So what I'd like to do is just show you two kind of really simplistic examples of these two conceptual approaches. And then we'll dive into some of the more complicated things that are in the modern reinforcement learning literature. So the first conceptual approach, where there are not that many data distributions, arises in contextual bandits. So here the setting is the time horizon is just 1. The action space is finite. And we're going to assume that the reward function, which is the expected value of the reward given the current state action pair, is well predicted by our function class. So there exists some function f star, which is it predicts the expected reward, and that actually lies in the function class script f that we're going to use. And so a very natural thing to do here is to collect n samples where you see the state, you see the action, you take the reward, you see the reward, but you take the action uniformly at random from your action set. And if you do this, again, the obvious thing to do is to try to predict the reward using your function class. So you solve this least squares problem, and you define the policy pi hat using this induced greedily with respect to your learned predictor. And in this setting, we can actually prove that the suboptimality of your policy pi hat is bounded by square root complexity of the function class over n times the number of actions. And what's going on here is that the number of actions is kind of the effective number of distributions in this problem. So each policy induces a different distribution over state action pairs, but all of these distributions are covered up to a multiplicative factor of cardinality of A by the uniform distribution over actions. And so in some sense, there's only cardinality of A distributions in this problem, and the uniform distribution covers all of them sufficiently. So this is sort of conceptual approach 1. But note that if we were to apply this to the multi-step reinforcement learning setting, the obvious way to do this, you would pay cardinality of A to the time horizon. So this would not meet our desired statistical goal. So that's approach 1. Conceptual approach 2 arises in a topic called linear bandits. And here, again, we're going to assume the time horizon is 1. We're going to assume that the starting state is fixed, and I'm going to suppress it from all the notation. And in addition to assuming that the reward function is well specified, we're actually going to assume that it's well specified by a linear function. So here, phi of A will be a known d-dimensional feature map that's associated with each action. And the expected reward for playing action A will be given by the inner product between some unknown parameter theta star and the known representation phi of A. In this setting, again, this is not super complicated, but in this setting, perhaps the obvious thing to do is to collect your data on a basis, or an approximate basis of your feature space. And if you do that, then we can show that the suboptimality is upper bounded by something like square root polynomial in the dimension divided by n. And note that here, because we're using linear regression, the complexity of the function class is D, and that there's no dependence on the cardinality of the actions. So what's going on here is that the function class, which are linear functions, somehow directly supports the ability to extrapolate from the basis to the entire space. So just by playing, action A1 and A2, I can infer the reward on action A3 because it's in the span of the other two. So this is conceptual approach number 2. And I just want to call out that actually a lot of these ideas first appeared in the theory CS literature. I think the first time I've seen these is from this paper by Auerbach and Kleinberg, where they introduced the barycentric spanner. This is a notion of an approximate basis. And then there's some other work that this sort of got picked up in the online learning literature and is now sort of pretty commonly used in the reinforcement learning. For the remainder of the talk, I'm going to show you how you can use some of those conceptual approaches in analyzing multi-step reinforcement learning problems. And I'm going to try and structure this in terms of this landscape of tractability. And hopefully by the end, you will understand what all these concepts mean. Just to tell you about the color coding, we know red implies intractable, and we know that there are RL problems that we should not expect to be able to solve, like the exponential tree. Yellow is statistically tractable, but computationally intractable. And blue is both statistically and computationally tractable. So let's start out with the low rank MDP with the known phi. This is going to be a setting where we can do linear function approximation. So we're going to do linear function approximation, and this is a setting where we saw that we can maybe use the extrapolation approach that I alluded to before. And what we're going to do is we're going to assume that there's some feature map phi that maps state action pairs into D dimensions, and we're going to take our function class to be linear functions in this feature map. And remember that well-specified linear functions directly support extrapolation. So the most basic question here is Q star being linear sufficient for multi-step reinforcement learning? And this, as far as I know, this question is still open, but the evidence is quite heavily leaning towards no. So there's been some recent work in the last 2 months or so that suggests that this is unlikely to be the case. And what these works are highlighting is some notion of error amplification. And so basically the lesson is that extrapolation is not the only issue. There are some other issues that arise when we think about multi-step problems. But those issues are sort of obviated when we make some additional dynamics assumptions, and that's what the low-rank MDP is doing. So the low-rank MDP, we're going to assume that the rewards and the transitions are actually linear in the features. So the reward function part is kind of straightforward. The fact that the transitions are linear in the features, what does this mean? It means that we can write the transition operator as a matrix, and it admits a low-rank factorization in terms of 2 feature matrices, and one of those is actually our embedding function phi. And in this case, we'll be able to see that we can actually do sample-efficient reinforcement learning. Note that this low-rank MDP assumption actually does imply that Q star is the linear function, and it's going to avoid some of the issues that those lower bounds are suggesting. So it's going to enable us to do credit assignment. So here's the algorithm. It's going to be an optimistic dynamic programming algorithm. So we're going to have collected some data, and we're going to do some computations on the data to discover a new policy, and then we're going to collect data with a new policy. And the computations that we're going to do are going to be dynamic programming from the last time step, capital H, from the back to the front, from the last time step to the first time step. And so we're going to create these Q functions, Q hat H for each time step H, from time step capital H onward. And assuming we have Q hat H plus 1, we're going to create Q hat H as follows. We first solve a least squares regression problem using the data that we have. And here we're going to learn a linear predictor, theta hat H, by trying to use our feature map to predict the immediate reward and the prediction that our Q hat H plus 1 function is making at the next time step. So this is just least squares regression. And this optimization problem, this least squares problem, is motivated by the recursive formula for Q star. So remember, Q star at a particular time is the immediate reward plus the prediction of the Q star value at the next time. And so we're trying to do exactly the same thing here. So we solve this least squares problem, we get a predictor theta hat H, and then we're going to use theta hat H to define our Q hat H function. So Q hat H is going to be the prediction made by theta hat H plus a bonus term, which we're going to use to ensure optimism. And then we're going to complete this dynamic programming. We're going to get Q hat 1 to Q hat H, capital H, and we're going to just collect data with the greedy policy induced by this sequence of Q hat functions. So in a very recent paper, Jin, Yang, Wang, and Jordan showed that this algorithm has a regret that scales as square root d cubed h cubed t in t rounds in the low rank MDP. And this algorithm is also computationally efficient. So what I want to do is show you a little bit about how their proof goes, because I think it highlights some of the key principles that we have been using to analyze some of these optimistic reinforcement learning algorithms. So the first thing is how do we use optimism? And this is an optimistic regret decomposition that's going to be extremely useful. So if Q hat is optimistic, it means that Q hat is pointwise greater than Q star. And if this is the case, then we can write the following inequality. So the left-hand side here is comparing the performance of the optimal policy at the current state with something that's like if we took the first action perhaps suboptimally and then behaved optimally from then on. And what we can show is that we can replace the first term, this Q star of x, pi star of x, with Q hat of x, pi hat of x via this optimistic property. And this is actually really great because on the left, we have the left-hand side includes some terms that use pi star's trajectory, which is stuff that we're not going to see because we're not executing pi star. And on the right, everything is kind of using pi hat's trajectory, which is stuff we are going to see because we're about to execute pi hat. So that's the first step. The next step is to write Q hat H in a particular way. So how do we construct Q hat H? Well, we added a bonus onto something, so there's a bonus term. And then we constructed the other part by doing regression. So the error term is going to be our regression error. And then the last term, which is kind of an inductive term, is what we were trying to predict with our regression. So this is a very nice way to write Q hat H. And the point is that Q star H also has a very similar inductive form. So when we write out Q hat H this way and Q star H in its inductive form, some things will cancel out. And what we'll get is that this error is bounded by the bonus, the error, and something that's happening at the next time. And the thing that's happening at the next time looks very similar to what we actually started with. So this is actually going to lead to a telescoping argument. And if the errors are upper bounded by the bonus, which we'll set the bonus in a way to ensure this, then what we'll be able to show is that the regret is less than something like the sum of the bonuses on the trajectory induced by pi hat, which we're about to collect. So this is the optimistic regret decomposition. And it's very nice. It's very clean. So we have to ensure optimism in order to apply this analysis. And ensuring optimism is, roughly speaking, the standard well-specified least squares analysis for linear regression. There are some technical details. I think one thing I want to highlight is that the fact that this regression problem is actually well-specified is guaranteed by the low rank assumption, and that's really important. And when you do this least squares analysis, you will see what form the bonus should look like. And once you have the bonus, there's a potential function argument. And this would roughly just say that the bonus cannot be large forever. And the way this works is that the bonus is something like a quadratic form in inverse covariance norm, where the inverse covariance is in terms of all the features you've seen so far. And the point is that if you incur a high bonus, then you're going to add a new feature into your covariance, and so you could not incur a high bonus in that direction again. And so the bonuses just simply cannot be large forever. Now, there's one open problem here, which is that this algorithm does not actually achieve the optimal rate for the low rank MDP. And we know what the optimal rate is, and we know there's an information theoretic algorithm to achieve it, but we don't actually have a computationally efficient approach. So this is a very nice open problem here. So that was the low rank MDP with the known feature map phi. Let me tell you a little bit about a slight generalization, which is the eluder dimension setting. So the eluder dimension is a more combinatorial notion that captures worst case extrapolation, which is very similar to what we're doing in the linear setting. So the way we define this quantity is through the notion of dependence and independence. So point Z is going to be said to be epsilon dependent on a sequence of points Z1 to Zn, roughly speaking, if the predictions on Z1 to Zn constrain the predictions on the point Z. So this means that if you take any two functions in your class and their predictions are very close on the previous points, then they should also be close on this new point. And the eluder dimension is the length of the longest independent sequence. And eluder dimension is really nice for analyzing these optimistic algorithms. It, roughly speaking, gives you a different potential function. So you do sort of the same optimistic regret decomposition, and then you can argue that if the bonus is large, then the point that you currently have must actually be dependent on just a few disjoint subsequences. So you're going to grow some independent subhistory, and these things just cannot grow forever because the eluder dimension is small. So this kind of potential function argument can give you root T regret rates for bandits. This was in a paper by Russo and Van Roy. And you can also get something for reinforcement learning, but you're going to require some more assumptions, kind of like how in the low rank MDP, we needed some additional assumptions to ensure that our regression problems were well specified. So now you might be asking, when is the eluder dimension small? And unfortunately, we don't know too much about this. So we know that it is small for linear and nearly linear functions. So linear functions are what you expect, and generalized linear functions are things like nonlinearity applied to a linear transformation, where the nonlinearity is relatively smooth. We also know that it is not small for highly nonlinear functions, like this rectified linear unit here. This is something I learned very recently from Jean Lee and Pratish Kamath. And so there's still something to ask here, which is roughly what nonlinear settings do admit small eluder dimension. So as far as I know, eluder dimension is the most comprehensive theory for distribution-free extrapolation, but unfortunately we don't really know when it applies beyond kind of linear settings. So that's basically all we know about how to use the extrapolation approach in multi-step reinforcement learning. What I want to do now is tell you a little bit about this other approach, this not too many distributions approach, and this will be formalized via this concept that we call the Bellman rank. So to do this, let's revisit the low rank MDP. Remember that here we're going to assume that the transition operator T admits a low rank factorization in terms of these functions phi and mu. So the key thing about the low rank MDP is that for any policy pi and any function g that maps states to the reals, we can write the expectation of g at time step h when we applied all the previous actions according to policy pi. We can unroll this expectation and write it in terms of the transition operator at the previous time. And then we can use the fact that t is low rank, and we'll get this nice inner product structure. So what's happening here is that this expectation of g induced by policy pi can be written as the inner product of one term, which is the feature map at the previous time when we roll in with policy pi, times another term that actually does not depend on pi at all. So this is like the integral over these mu measures of this g function. And so if you step back a little bit, sort of what this is saying is that every roll-in distribution, every distribution that can be induced by policy pi, is kind of parameterized in a d-dimensional space. So there are not that many distributions in this problem. And so we're going to use this, this idea to create a new complexity measure that will allow us to capture the fact that there are not that many distributions here. So here's the key definition. This is called the average Bellman error of value function f induced by policy pi. Typically, I'll just call this the average Bellman error. So here, this is the scalar, and what it is it's the expected value of the residual between f's prediction at time step h and f's prediction at time step h plus 1 on a data distribution induced by policy pi. So I'm going to roll in to state xh by taking actions according to policy pi, and then I'm going to take the next two actions, ah and ah plus 1, by the greedy policy induced by pi f, greedy policy induced by the value function f, and I'm going to look at what f predicts at time step h and subtract off the immediate reward and what f predicts at time step h plus 1. Remember that Q star satisfies a very similar recursive relationship. So this is sort of a hint as to why this is the right definition. And so this is going to be the key definition. Just as an aside, we'll see it in a bit later. There's another version of this where the H action, A sub H, is drawn from the roll-in policy instead of the evaluating policy. Okay, so this is just some strange definition, and what this calculation at the top of the slide is basically saying is that this average Bellman error admits inner product structure, where we can write it as a d-dimensional inner product, where the first term depends only on the policy pi, and the second term depends only on the function f that we're trying to evaluate. And this is actually true for any function f. So this is kind of motivating writing things in terms of a matrix. So I'm going to collect all of these average Bellman errors induced in a matrix where the rows are going to be indexed by policies and the columns are going to be indexed by action value functions. And in each entry is going to be the average Bellman error of action value function f induced by policy pi. And the complexity measure is just going to be the rank of this matrix, or the max. There's one of these for each time step h. It's going to be the max of the ranks of these matrices. And you can kind of see by this low rank MDP example that this is going to capture the fact that there are not that many distributions in this problem, because in the low rank MDP, the rank will actually just be the dimension. But as we'll see, it will also capture the extrapolation approach. But first, maybe I should convince you that this is sufficient. And so here's going to be the main theorem for this part of the talk. Let's assume that we have realizability, or that Q star is in our function class that we're going to use. And let's also assume that the Bellman rank is at most m. Then what we can show is that we can learn epsilon suboptimal policy using something like m squared, number of actions, horizon cubed, statistical complexity over epsilon square samples. And with the other definition that I alluded to, you can eliminate the dependence on the number of actions. And in a pretty recent paper, some folks were able to show that you can actually get square root t regret rates, which is quite a non-trivial result. So this is the main theorem. And what I'd like to do is I'd like to tell you what the algorithm is, show you a little bit about how the proof goes, and then sort of tell you about when this quantity, this Bellman rank, is actually small. So the algorithm is called Olive, and it's an iterative algorithm, and it's kind of a version space algorithm. So we have a set of functions script f, and what we're going to do is we're going to try to eliminate functions from that script, from that class, that we can prove to not be Q star. And at the end, we'll have maybe a few functions, and one of them will sort of induce a good policy. So in each iteration, we're going to do a couple things. The first thing we're going to do is we're going to look through our set of surviving functions to find one that maximizes its prediction about its own policy at the start state. So this is going to be a kind of global optimism. This is going to be an optimistic guess for the optimal value V star. The second thing we're going to do is we're going to collect trajectories with the policy induced by the function we just picked and estimate its actual value. Next, we're just going to check if the value we actually are picking up is about the same as the value that this function is actually predicting. So this is just going to be checking if our guess is accurate. If it is, we're going to say we're done, and we're just going to output the induced policy by our current predictor. And if not, we're going to evaluate these average Bellman errors on the data distribution induced by the current policy that we have, pi sub f hat. And we're going to eliminate any function for which the Bellman error is non-zero. And then we're going to repeat. That's the whole algorithm. And so this is going to be like refining the search space. We're going to eliminate some functions, and so we're going to make some progress. Okay, so the first observation is that each iteration does not require too many samples. We're only collecting data with one policy, and we can evaluate all these Bellman error, average Bellman error quantities relatively efficiently. So the key question is, how many iterations do we need? Okay, and so here's sort of how the analysis goes, and the key part will be how many iterations do we need. But first of all, the first claim is that Q star will never be eliminated. And the reason is that Q star satisfies the Bellman optimality equation that I mentioned very early on in this part of the talk. And therefore, the average Bellman error of Q star is 0 on any roll-in distribution for any roll-in policy pi. Okay, so that's great. So this claim plus the way we choose the policy that we use in each iteration optimistically implies that we'll be near optimal upon termination. Because we're predicting a value that's higher than V star, and we're achieving that value. So we have to be near optimal. Okay, so claim 2 is a sort of performance decomposition lemma, and this is an equality. So the value that function f predicts about policy pi f minus the actual value that policy pi f gets in the real world can be written as the sum of the average Bellman errors of value function f on the data distributions induced by pi f. And this is equality. So this implies that f hat will always be eliminated, because the fact that we don't terminate implies that the left-hand side is very big, which implies that one of these Bellman errors is non-zero. But it actually implies that many, many more functions will be eliminated. So what the next proof by picture will show you that the number of iterations is actually quite small. So here's the picture. Let's write down this Bellman error matrix. And Q star is one of the columns because we have realizability. And claim 1, or the fact that Q star has 0 Bellman error everywhere, means that this whole column is always 0. Now we've collected data from two policies, pi 1 and pi 2, and we're going to, the current policy we're evaluating is pi f hat, and the current action value function is f hat. So this is where all the key action is going on in this matrix. Okay, so the fact that f hat has survived so far implies that on the entries on pi 1 and pi 2's data distribution, f hat has 0 Bellman error. So these two entries are actually 0. Now, the fact that we don't terminate implies that the Bellman error here induced by pi f hat is not 0. And therefore, the row indexed by pi f hat has to be linearly independent from the rows indexed by pi 1 and pi 2. And this can only happen m times because that's the rank of this matrix. And we can do this for each time step h, and so the total number of iterations will be at most mh. Okay, so this is like almost the argument. The real proof has to do something more volumetric because rank is quite a brittle notion. And so we do something that's quite similar to what you might be familiar with in the ellipsoid proof. So that's Olive and why the Bellman rank is a sufficient notion for statistically tractable reinforcement learning. What makes the concept of Bellman rank interesting is the fact that it turns out to actually be small in many models that have been independently studied in isolation in the reinforcement learning community. Some of these models include the Tabular MDP, which John talked about in the first part of the tutorial, the block MDP, which I'll tell you about in the next slide and which we'll cover in detail in the fourth part of the tutorial, the low rank MDP, which we already saw, another setting that admits linear function approximation, and actually many other models. We can also check that in the exponential tree, the Bellman rank is the number of actions to the time horizon, so nothing is going wrong over here. This setting is certainly intractable. So I want to just tell you a little bit about a couple of these. I'll tell you about the block MDP, we'll just review the low rank MDP, and I also want to tell you about this linear completeness setting. The block MDP is a latent state space model in which there's a discrete hidden state space, and the agent does not observe these hidden states. And instead, the agent will observe some observations that are generated by emission distributions associated with each hidden state. So the application to keep in mind is a navigation setting in which the agent at any time is in a particular position. The agent does not observe its position and instead observes an image from a camera mounted on its head. And so the agent looks at the image, takes an action, and due to the fact that the agent is in a particular position and takes a certain action, the position of the system will change, and then the agent will see a new image. Now this setting, it's pretty easy to check that the Bellman rank is at most the number of hidden states, and the reason for this is that each roll-in policy will induce a distribution over the hidden states And the Bellman error of the value function can be written in terms of the averages over the observations coming from each hidden state. So the Bellman rank is just the number of hidden states, and I just want to emphasize that this is actually true for any function class script f, any set of value functions. And so this really supports quite generic nonlinear function approximation. Now note that olive also requires realizability of the optimal function q star, and so this model is actually not really supporting memory. So if you're familiar with these partially observable processes, this model should not really be thought of as a POM-DP, because the q star function should only look at the current observation. And we'll talk more about this model in part 4 of the tutorial. The next model is the low rank MDP, which we've already discussed before. Here, again, it's a calculation that we've already done to show that the Bellman rank is the rank of the transition operator. And again, this is true for actually any function class script f. So the low rank MDP, again, also actually supports quite generic nonlinear function approximation. And we'll talk about this a bit in part 4. So we've been studying a setting of the low rank MDP where you actually don't know the feature map phi. And this Bellman error calculation, this Bellman rank calculation actually shows that this setting is also statistically tractable. The last setting I want to briefly cover is this linear completeness setting. This is a setting that people have been studying recently for linear function approximation. And it operates under an assumption that's a bit weaker than the low rank MDP. So the assumption in words is that the Bellman backup of any linear function is linear in the current features. So let me just go through this. So we're going to do linear function approximation. And what we're going to try to do is we're going to try to write the immediate reward plus the predictions of a linear function at the next time as a function of the current time. That's called the Bellman backup operator of your prediction function theta. And the linear completeness assumption is that this Bellman backup is actually a linear function in the current feature map. This is a standard assumption in the analysis of dynamic programming algorithms. It really lets us do credit assignment. And we can verify that the linear completeness setting actually also has Bellman rank that's equal to the dimension of the feature map. And the calculation is as follows. So the Bellman error induced by policy pi can be written as, for a function theta, can be written like this. And we can use this linear completeness property to write the reward plus the prediction at the next time as a linear function of the current feature. That's what I'm doing here. And finally, we can note that theta and w do not depend on the policy pi. And so we can push the expectation inside. And just note that I'm actually using the alternative definition of Bellman rank, in which the current action is taken by the role in policy pi. So this calculation I think is quite interesting because it really exploits the structure of the function class script f, which is assumed to be linear with the completeness property, and it doesn't really exploit the dynamics of the environment. So I feel this one is more like the extrapolation argument for linear classes, which has been studied recently in some pretty cool work. Let me also just say that this kind of setting, at least as far as the Bellman rank is concerned, it doesn't seem like it supports nonlinear function approximation, even if you have this completeness property. So to summarize, we can see through some of these calculations that the Bellman rank captures the structure of the environment in this not too many distribution sense, and the structure of the function class in the sense that if the function class supports extrapolation, then we can also get low Bellman rank. So let me just summarize what we've discussed for value-based methods. We saw some linear methods where we see that positive results seem to require something more than realizability. For example, they might require that the MDP is low rank, or they might require this completeness condition. And the current thinking is that realizability alone is insufficient. And there's been some really cool recent progress here, but this is still kind of an open question. And we've also seen some nonlinear, some combinatorial parameters that support nonlinear methods, such as the Bellman rank, but these seem to require some kinds of dynamic assumptions. For example, like we're in a block MDP or a low rank MDP. And popping up a level, we saw these two conceptual approaches for handling distribution shift. The first is this not too many distributions approach, which arises in contextual bandits. And the second one is this extrapolation approach, which arises in linear bandits. And some open questions here are whether neural networks or other interesting nonlinear classes enable extrapolation, and what the optimal rates are for these extrapolation approaches. In the last part on information theory, I want to talk about some model-based reinforcement learning methods. I'll also discuss the factored MDP and this other combinatorial notion called the witness rank. The factored MDP is a model for reinforcement learning with a combinatorial state space. The state is modeled as a d-dimensional discrete vector, and we assume that the transition operator factorizes in terms of a sparse probabilistic graphical model, where each coordinate of the state at the next time depends only on a few coordinates of the state at the current time and the action. We can do a parameter counting calculation and see that in the unfactored representation, the number of parameters required to represent the transition operator is far more than what it may be in the factored representation. And indeed, it is possible to obtain regret bounds that scale only with the number of parameters required to represent the transition operator. However, on the computational side, basically everything is hard. So planning is known to be computationally hard, and it's not even possible to represent the optimal policy using a polynomially sized circuit. So this leads to a very nice modeling question, which is about what combinatorial models are computationally tractable for reinforcement learning. There's also something interesting on the statistical side, which is that we can show a form of separation between model-based and value-based methods. So we're able to show that for value-based methods, reliability alone is actually not sufficient to achieve sample complexities that scale with the number of parameters in the process. Stepping back a bit, we're also able to develop a complexity measure for model-based reinforcement learning that is very analogous to this notion of Bellman rank. For model-based RL, the natural assumption is that we have a class of candidate dynamics models, script M, and that our true transition operator lives in this class. Analogously to the development of the Bellman rank, we're going to define a way to evaluate if a model is good or bad on a data distribution induced by some policy pi. This is this quantity that we call the witness model misfit. And we're measuring here the total variation error between the model M that we're trying to evaluate and the true transition operator T on the state distribution induced by policy pi at time step H. Just like for Bellman rank, we can define the witness rank to be the rank of these matrices. And we can show three interesting facts. So the first is that the witness rank is always smaller than the Bellman rank if we take the set of action value functions script f in the definition of Bellman rank to be those induced by the model script m. We can also show that small witness rank and model-based realizability are sufficient for sample-efficient reinforcement learning, and that for factored MDPs, the witness rank is at most a number of parameters. So the conceptual takeaway here is that model-based methods require stronger realizability conditions because model-based realizability actually implies value-based realizability, which we were using before. On the other hand, the factored MDP demonstrates a situation where model-based methods can provably succeed, where value-based methods provably fail. So that's all for part 2 about information theory. And up next, we're going to have Alek Agarwal talk about some policy optimization methods, and then John will return to talk about an algorithmic approach based on latent dynamics modeling. Thanks.
Okay, so in the results Akshay presented so far, we saw when things are possible statistically, although we don't always get computationally viable algorithms. In the next two parts, we'll focus more on getting computationally efficient techniques. And I will focus on algorithms that are designed with an optimization perspective, thinking of reinforcement learning as an optimization problem. And John will then talk about a different class of algorithms. So the optimization-based approaches to reinforcement learning are not really new. They've been around for a while, and they really think of reinforcement learning as an optimization problem and try to do end-to-end gradient-based optimization for directly optimizing the objective, which is the reward of the agent. And these approaches in particular have been quite popular empirically because they tend to play well with modern deep learning architectures, and as a result have been used in all kinds of domains ranging from all types of games and as to physical systems like robotic manipulation and even rally cars. And just like at this point we feel that deep learning is a pretty essential tool in our arsenal for supervised learning, we expect deep learning and policy optimization together to be a critical component of modern reinforcement learning systems. But these methods have their own sets of challenges. So they don't quite explore the domain in the same systematic manner that many of the algorithms Akshay talked about do, and that results to lack of robustness often in their application, which then we have to try and address by a variety of handholding and heuristics in practice. And the goal of developing theoretical foundations for these methods is to try and improve them, or to understand the lack of robustness so that we can overcome it. And that's going to be the goal of this tutorial. So I'll start with some preliminaries and then talk about convergence properties in various settings, and finally address the lack of exploration in these methods. First thing we have to do in any optimization problem is set up an objective. So for this part, we'll focus on the discounted Markov decision process setup. We have the same states, actions, rewards, and transitions as before, but instead of using a finite horizon, now we'll take an infinite horizon. And the reward we get at time t is going to be discounted by a factor gamma to the t, where gamma is something in 0, 1. So we care less about very delayed rewards than we care about more near-term rewards. And the effective horizon we get this way is 1 over 1 minus gamma, as John had described before. The optimization problem is to find a policy which has a large expected discounted reward when we take actions according to the policy. And we now explicitly index the policy with the underlying parameters theta, so that we can start viewing this as an optimization problem over theta, the policy parameters. And we can ask if we can run iterative optimization algorithms like stochastic gradient methods to find an increasingly better solution, set of solutions theta t over iterations. Whenever we encounter an optimization problem, there are some basic questions we must ask. First, what is the optimization landscape? Is the problem globally convex or concave? If not, what can we say about the local minima or saddle points? Since this is reinforcement learning, how do concepts like exploration and the policy parameterization interact with this landscape? And of course, the most important final question we would like to address eventually is the convergence and sample complexity properties of these gradient-based techniques for reinforcement learning. So since we want to do gradient-based optimization, it is helpful if things are differentiable. And the deterministic policies Akshay talked about in the previous part present a hurdle there. So instead, we look at stochastic policies now, which map states to distributions over actions. Because these policies will generally tend to be smooth functions, differentiable functions of their parameters, and are hence amenable to gradient-based optimization. And a particular form of the policy we'll actually focus on today is what's called the softmax form, where we take our state action, we map it through some function f theta as a function of parameters theta, and then pi theta of a given x is just proportional to x of that function. And based on what function you use, you get different styles of policies. So when the number of states and actions is small and finite, you can just say you have one parameter per xa, and f theta is just equal to that parameter. And this is a fully expressive policy class, meaning that any policy you want to express, you can express in this parameterization. When you have large state and action spaces, now we might want to make things more parametric, and maybe we define some features on states and actions, and the function f theta can be a linear function in that feature, or it can be something more complex like a neural net. In other situations, like in control problems, like with robotics, often it's very natural to think of the policies as having some Gaussian distribution over the state action space. And often this is done by, again, having some features over state action pairs and maybe the mean of the Gaussian is parameterized through some complicated function g theta, which can again be linear or nonlinear based on the problem. So the bottom line is that these softmax policies can be quite flexible, quite expressive, and we'll focus on this type of policy parameterization today. Now, given a policy, it always induces a distribution over states. So maybe you start in some initial state x0, you take actions according to pi, that's going to induce a distribution over x1 and x2 and x3 and so on. And you can take these distributions at individual time steps. You can average them, you can accumulate them using the discount factor gamma to the t, and scale with 1 minus gamma to turn this whole thing into a probability distribution again. If the initial state is drawn from a distribution mu, I will use the subscript of mu in the state distribution of pi. And we will sometimes also extend this distribution to state action spaces instead of just over states. The final concept we'll use is that of the value function of a policy, which is the expected reward I get when I choose all actions according to my policy pi. And in terms of the state distribution, it can just be written as the expected reward when states and actions are drawn according to d pi. There is also the Q value function of a policy, which is if I start in X, I take the first action to be A, and then subsequently follow pi for the remaining actions. How much reward I get, and Q functions follow this linear relationship with the V functions. And you saw Q star and V star before in the information theory part, and these are just extending the concepts to arbitrary policies now. Okay, so with these definitions, we can now start talking more concretely about policy gradient methods, which take this optimization objective we have for reinforcement learning. And basically, the simplest thing you can do is to take the gradient of this objective with respect to the policy parameters theta and update in the gradient direction where Vt is the value of the policy corresponding to theta t. So whether you can run this algorithm or not depends on whether you can evaluate these gradients in some easy manner. And the observation that powers this entire family of algorithms is this very nice result that shows you can indeed evaluate these gradients in a nice manner. So the gradient can be written as this expectation where we draw states and actions from pi theta. And inside the expectation, we've got this first part, which is a fully known function. I can write it down in closed form. And the Q function of pi theta. This is not something I generally know in closed form, but what you can show is that this entire expectation, you can write down an unbiased estimate of it if you have trajectories sampled according to the policy pi theta. So what you do is you take a trajectory, you choose a random stopping point and declare that the state and action there to be the XA that you will use. And you look at the discounted reward in the remaining trajectory and use that as an unbiased estimate of the Q value here. And just this very simple estimator that you can show to be an unbiased gradient can then be used to run a stochastic gradient descent, which was introduced under the name called reinforce by Williams in his classical 92 paper. And since then, there's been a flurry of algorithmic work. So there is the actor-critic algorithms that were introduced by Konda and Tsitsiklis in 2000. And people have incorporated all kinds of improvement from optimization literature, whether it's about first region methods that constrain the size of the step we take and lead to algorithms like TRPO and PPO. Variance reduction tricks to recenter the gradient with control variate techniques, additional regularization schemes such as these entropy regularized soft actor predict type methods that are now performing quite well in many empirical problems. On the theory front, since we are doing stochastic gradient descent, convergence to stationary points is almost immediate under appropriate smoothness conditions in the objective, basically by classic Robbins-Monroe. Beyond that, things get a little bit tricky. So if we don't worry about global optimality for a moment, what people often do is they have some reference policy pi0 in mind, and they just want to discover a policy with in our parameterization that is going to be roughly as good as pi0 or better, not necessarily globally optimal. And this has been studied quite a bit in the imitation learning literature with some very nice theoretical and empirical results. Situation for global optimality is trickier and was first, this was introduced in this 2002 paper of Kakade and Langford, who described a policy optimization algorithm called conservative policy iteration, or CPI, and show that under certain assumptions on the exploration that the algorithm is being provided with, as well as the policy parameterization, it can find a globally optimal policy. It can converge to a globally optimal policy. In fact, a lot of what we will initially start with and build on today is extending similar kinds of ideas to policy gradient methods. CPI by itself is not a policy gradient method, although it is very much related to the type of improvement of policies that iterative improvement that we are trying to do with gradient-based methods. But we will extend some of this reasoning to policy gradient methods first, and then build upon it for more complicated cases. Okay, so since we are trying to do first order methods, it's good to start by trying to understand the optimization landscape. And the first thing we can observe there is that there are MDPs where our objective is not a concave function of theta, meaning we're not guaranteed a unique global optimum in our maximization problem. Things get worse from there. You can build MDPs like the chain here, where you start in a 0 all the way to the left. The only time you get a reward is when you get to this state all the way at the right. And if you try to move to the right, most actions will take you back left. And the only time you get to this nice rewarding state is by choosing a particular careful sequence of actions. This is very much like the search tree example, actually, that Akshay was showing you in the previous John was showing you in the first part. And what you can argue is, in these types of MDPs, there are policies which basically reach this rewarding state with an exponentially small probability in the length of the chain. So these policies don't really get any significant reward. But if you look at their gradients with respect to the parameters, the gradients are vanishingly small, exponentially small again in the length of the chain. And it's not just the first order derivatives or second order derivatives that are small. If the length of the chain is h, roughly like h over 4, so a constant fraction of the length of chain, gradients even at higher orders will be vanishingly small. So what this means is, if you're running any kind of gradient method that's trying to make the gradient small, or even the higher order derivative small, that's not necessarily going to find good policies. And this is not a statistical issue. This is not something you can fix by collecting more data. This is really happening with exact gradients. And because of the fact that the only time you get a signal in this MDP is when you go all the way to the right, and these policies that witness this lower bound have a very small probability of going to the right. So even the exact gradients are extremely small. This also starts to suggest an interesting contrast between the optimization landscape in supervised and reinforcement learning problems. In supervised learning, we are getting pretty used to non-convex optimization typically being solvable in general using gradient descent, not being sensitive to initialization, saddle points not being a problem. You can maybe, if you get stuck, look at a higher order derivative to escape, things like that. Not true in reinforcement learning, where you can have really this large, very flat regions where you have many, many orders of gradients vanishing. And these small gradients happen due to bad exploration. Like in the chain, they happen because you start on the left and you have a really hard time getting to the right. The good thing about the no problem is we can start thinking about solutions to it. So maybe our agent doesn't have to start all the way to the left. Maybe we can find a way to help our agent by not starting it all the way left, but maybe in a uniform distribution over states in the chain or something. Or maybe it doesn't have to wait to go all the way to the right to collect a reward. Maybe we can bring the reward closer to the initial state somehow. So the second style of approaches are studied in what's called imitation learning or reward shaping, two different approaches, which we will not have time to cover today. We will instead mostly focus on first trying to understand what constitutes favorable state distributions for policy optimization, and then how to construct them. So now that we are, the way we're going to reason about the quality of initial distributions is, remember, we still have this optimization problem where we care about an initial state x0. But for the algorithm, we'll assume we can start the agent in some distribution mu over initial states, such as maybe the uniform distribution over the states in this chain. And what that does is now in our gradients, in our expectations and so on, everywhere we look at the state distribution of the policy, it becomes a function of mu. And if mu is sufficiently dispersed over the state space, maybe we can say something nicer about the convergence properties of these methods or the informativeness of the gradients. And with that in mind, we'll now ask, okay, with this mu-based modification, what can we say about the convergence properties? What role does the distribution mu and the policy parameterization play? And can we use this understanding to design good distributions mu algorithmically somehow? So we'll start by examining the convergence properties of policy gradient methods in tabular settings. And the goal here is to not get new algorithms for tabular MDPs. We have algorithms that work in that setting. But the goal is to start understanding policy gradient methods in the simplest setting before moving to more complicated ones. Okay, so for the tabular setting, we'll now remind ourselves that the policy takes the function from here where we have one parameter per state action pair. And we're looking at the vanilla policy gradient algorithm. And if the probability of every state is non-zero under the distribution mu, then for appropriate step sizes, we do find a globally optimal policy asymptotically as t goes to infinity. And we can get some rates as well for this under, however, significantly stronger assumptions. So on the one hand, this should not be surprising. We start from a non-zero probability over all states. We have non-zero probabilities over all actions by this functional form because thetas are finite. And so we are going to try out everything, and hopefully we should find something globally optimal. On the other hand, remember that we are trying to converge to an optimal policy, which is going to be deterministic, which means a lot of the action probabilities are going to start going to zero. And as a result, the quality of our exploration will degrade the more we converge. So now we start getting this competition between our convergence and our exploration, and becomes a question of which one is going to be faster. So that's an exercise in real analysis, which you have to be careful with. But in the end, you do get convergence to global optimum. However, the convergence is quite slow, exactly because this exploration is becoming worse and worse as you get closer to a globally optimal policy. And we in fact conjectured that the convergence is probably exponentially slow in this number of states or number on the horizon in the worst case, although that's purely an intuition from our current proof. And intuitively, all this is happening because we are really doing this optimization in a fairly ill-conditioned setting where there are these parameters near our optimal solution that we are trying to get to, where the space looks really flat and our gradients are extremely small. And when we find ourselves in ill-conditioned problems, natural thing we try to do in optimization is to improve the conditioning of our optimization landscape, perhaps by preconditioning the gradients, right? So multiplying them with some appropriate preconditioning matrix. And one such algorithm in the optimization literature is natural gradient descent, which uses a Fisher information-based preconditioner. This was introduced to reinforcement learning by Shyam Kakade under the name of natural policy gradient and has inspired many practical methods that people now use. Rather than showing you the general form, I want to describe the more specific form it takes for just these tabular parameterizations, where we have one theta per state action pair. So there we simply update the thetas linearly based on the Q function of the current policy. And the policy probabilities themselves get this exponentiated rescaling, which is a very familiar multiplicative weight updates for many of us. That's commonly used in the TCS and online learning literature. And this should be potentially promising because these multiplicative weight updates have a lot of theory backing them in many different situations. Except we have to be significantly more careful here because we know that we are in a non-concave maximization setting. But nevertheless, this is a familiar object for us. Nevertheless, you can analyze this update rule and provide a pretty strong guarantee for it, in fact. So without any requirement of an exploratory initial distribution, mu can just be concentrated on the initial state x0 that we care about. This natural policy gradient will converge to a near optimal policy at a 1 over t rate after t iterations, with no explicit dependence on number of states, number of actions, how well mu is exploring. It's just, it can be focused on one state, the mu itself. It's completely dimension free, right? Which is much stronger than the situation we were finding with vanilla policy gradient. So this style of update rule and its analysis was first pioneered in this very nice 2009 paper of Eyal Evendar, Shyam Kakade, and Yishai Mansour, and has seen a flurry of more recent interest. Of course, this does require that we have exact gradients, or in this case, know the Q function of the policy pi t exactly. If we are doing this with samples and have noise, then the noise does interact with how exploratory mu is, and all of those issues still come back to haunt us regarding whether mu is sufficiently exploratory or not. But rather than trying to flesh all of that out in the context of tabular representations, I first want to now move to more general representational settings, and then we'll talk about how statistical issues come up. Before we go there, I want to give you a little bit of an intuition about how this analysis is carried out. And it's based on this very useful lemma called a performance difference lemma that was introduced in Kakade and Langford's 2002 paper. So effectively, this lemma is a way to take the difference between values of two policies and rewrite it as a telescoping sum. And it's handy for us because, well, we are interested in regret. So we can think of this first policy here as something like pi star, the benchmark we want to compete with. We can think of pi prime as something like pi t, my current iterate. And now this is looking like regret. And it's giving me a way to expand regret. And what we can actually show is the multiplicative updates we are doing amount to fixing this, of course, as pi star, fixing this part and updating pi t plus 1 to optimize the action distribution. And that's really nice because that part is just linear in the policy pi. And we understand multiplicative weight updates, what they do for linear optimization. So we can follow that analysis, and that gives us a 1 over root t regret almost immediately. To get 1 over t, you have to do some more work to lower bound per step improvement based on certain smoothness properties of the objective. But the analysis is quite clean and simple. So now we want to take these intuitions and apply them to more complicated settings with large states and actions. And we'll start with linear parameterizations, where we have some features phi that we define on our large state action space, and the policies are linearly parameterized using some theta. We want to compete with the best linear policy, meaning the policy with the best, let's say, non-bounded parameters in this linear class. So first thing I have to tell you is what the NPG updates look like when I go to these more general linear policies now, because I only showed you the updates for the tabular form before. And they continue to look somewhat similar. So now you will have, it turns out, some update direction WT, and thetas will evolve in this, again, linear manner with WT. And the policy will, again, evolve in a multiplicative manner, but rather than decoupling across states and actions, now it will be a function of WT as well as the features. And what is WT exactly in this case? So it turns out the ideal W that we would like to use here can be defined, or the ideal W that NPG would like to use can be defined as a solution to a least squares problem, where we take states and actions drawn from pi t after starting in mu, and we try to fit the q value function of pi t as a linear functions with features phi. And WT star is the best linear fit in this problem. And if we had WT star and use it, this would be exactly equivalent to running natural gradient descent for reinforcement learning. Otherwise, you use some other WT and pay a price for the error between WT and W star that we will quantify. And to do that sort of error tracking, it would be useful to give a notation to this least squares loss. So we use L of W parameterized by the policy through theta t and the state action distribution dt. And we'll see this loss come up in the next few slides. So the algorithm we can, of course, also extend to the more general nonlinear settings, where again we have some update direction WT and the thetas evolve linearly under it, and our policy now has this more general form as a function of theta. And the main thing we need to address now is, for the regression problem, we don't have some obvious features lying around anymore. There are no phis. And what phis get replaced by, it turns out, are the gradients of f with respect to theta, or more generally, the gradient of the log pi theta with respect to theta. And again, you define WT star as the best fit in those features, which are now changing from policy to policy, the features, right? And then if you use WT star, you exactly get natural gradient descent for this policy class. We'll start by talking about convergence for the linear parameterization, which is governed by three main quantities. So the first is simply how well does WT approximate WT star in the sense of the regression problem that we care to solve. And we will denote this accuracy by epsilon stat. This should go to 0 as we use more and more samples to fit our least squares problem. The second quantity, which is a bit trickier, is, so WT star, remember, is the best linear approximation for QT under the distribution dt. Now this quantity, what it does is it replaces dt with a different distribution d star and asks, well, how good is wd star under this other distribution where d star is the state action distribution of the optimal policy that we want to compete with. So intuitively it asks, is your update direction going to capture the value of the policy well on the state distribution of other policies too? If not, it turns out you might have a problem. And this part is a bit more unique to reinforcement learning because there is no fixed a priori distribution over data that we work with. The third quantity, like before, measures how well mu explores the state action space. But now, since we have features, we capture this exploration in the feature space. So we look at the feature covariance matrix, phi transpose, that the distribution mu induces in expectation. And roughly, we want the largest eigenvalue of this covariance matrix to be large. Smallest eigenvalue of this covariance to be large. More generally, you can talk about relative notions to condition numbers relating d star and mu, but the simple intuition for smallest eigenvalue is quite adequate. So in terms of these quantities, we can now give a convergence result for NPG with these linear policies, where the first term goes down to 0 as 1 over square root of number of iterations. So this is a slower rate than what we saw in the tabular case. And the reason we do it this way is that getting a 1 over t requires some making some really strong assumptions in the more general case. The second term is governed by the statistical error relating WT and WD star, as well as how well mu explores the state action space. So the one nice thing you can show is that there is always a way to design a mu, irrespective of how large the state space and action space are, as long as they are embedded in a d-dimensional feature space. You can design a distribution in that feature space, mu, such that kappa will be at most order dimension. And this can be done using, for instance, the classic Lanajoy ellipsoid construction. So kappa you should think as a dimension-based quantity. And epsilon stat will depend on the number of samples you use to fit the least squares problem. So it will go down at something like 1 over root n. And finally, we have this transfer error term. So let's start by asking when this transfer error term is small or is 0. And if the Q function of every policy can be expressed as a linear function at every state and action, then of course I can keep shifting distributions around, put different distributions over states and actions, and there's just one weight vector for every policy, which is pointwise good at predicting Q values. Then this transfer is always going to be 0. And this happens exactly in tabular MDPs and low rank MDPs with features phi that Akshay talked about in the second part. And in these cases, epsilon bias goes away. And when epsilon bias goes away, and also when the statistical error is 0, that is if I have exact gradients, then the dependence on kappa goes away, and I recover the very nice and clean rate that we saw in the tabular case with exact gradients. And more generally, what epsilon bias measures is basically how good are your features phi in capturing the value of the policy you have. So it's a representational quality measure. And you can extend these results to the more general nonlinear setting, except the quantities like bias get a bit more involved. So we're going to skip over that today. The final thing I want to say about this transfer error concept is, of course, when we are trying to relate error between two distributions, the fitting distribution dt and some other distribution D star. One way you can transfer regression errors is by doing kind of a point-wise likelihood ratio relating, right? And you can ask, well, what is the largest possible likelihood ratio you incur at some state action pair relating D star and DT or D star and mu? And it turns out when you're in a setting where you're not actively exploring, but you just have data given from some a priori distribution mu, then these types of conditions are pretty, these types of density ratios are pretty common in the reinforcement learning literature. And the nice thing is that the type of dependence on these ratios we get in these policy gradient methods is the nicest in amongst all possible algorithms we are aware of currently. And that's because these policy gradient methods, because they are doing first order optimization with small step sizes, tend to update the policy slowly. So you update the policy a little bit, you collect some fresh data, you update the policy again, collect some fresh data. Whenever your policy changes, you go and collect data. And so you don't, you're always getting a good glimpse of the state action distribution that you're currently under. And that's a very nice property of these methods compared to other methods based on Q-learning that are more closely related to what Akshay talked about, for instance. It's, of course, for these transfer error type concepts, currently we just have various isolated examples for when these notions are small. And it'd be good to have a more comprehensive description of what are the various conditions under which these errors can be controlled. Okay, so having understood how the exploration enters the convergence properties, we now want to ask if we can design good exploration distributions mu algorithmically, and that's the last thing I'm going to talk about. And I'll focus attention on linear parameterizations, where we know we want to take the feature covariance matrix that our distribution mu induces and make this matrix well conditioned, make it have a large smallest eigenvalue. And one way to do this is we can try to find policies that reach all kind of diverse directions in our feature space, and then combine these policies together by, let's say, mixing them uniformly in a mixture. Of course, you have to identify such policies, and we provide a way to do this in an algorithm called PCPG, policy cover policy gradients, that we came up with recently. So policy cover here exactly refers to these exploratory policies that go to diverse directions in the state action space. And we build this set iteratively. So at iteration I, let pi I be the current policy cover. Then we define a uniform distribution. So we'll just pick up a policy uniformly from this set each time we want to collect some data. Now, what we do is for every state action pair, we look at its features and we ask, what is the quadratic form with these features in the inverse covariance matrix of rho I? Now, if you remember LSVI UCB before, this should look similar. They were using a similar quantity for a bonus. The idea is when this quadratic form is small, rho I has a reasonable probability of visiting directions like phi of xa. So we mark this direction as known, or this state action pair as known. We know how to get there. If it is not known, we give ourselves an exploration bonus for finding this new direction. So we would like to get to this direction because rho I does not get there currently. And this is very much like the bonus LSVI UCB gives out. The difference is we now take this bonus, we add it to our original MDP's rewards. We take rho I as the initial distribution mu, and we run NPG with this initial distribution and this bonus augmented reward, and find the policy pi I plus 1 it converges to, and add this policy to the cover and repeat this whole process, right? So now you can see we are algorithmically constructing increasingly, hopefully, exploratory initial distributions, and hope that at some point we've explored all the directions, in which case the previous guarantees can kick in and we would have found a near optimal policy. And indeed, when our MDP is low rank with features 5, we can show this happens. So for low rank MDPs, PCPG does find a near optimal policy using both samples and computation, which are polynomial in the dimension D, or if it's infinite dimensional, you can generalize to something called intrinsic dimension, if the features live in an infinite dimensional Hilbert space, for instance. So it's polynomial in dimension in 1 over epsilon in the effective horizon in a non-parameter W and log 1 over delta. So all relevant parameters. You can extend the result beyond exact low rank MDPs by analog of the transfer condition we saw in the previous segment. And there has been a fair bit of interest in this style of algorithms recently, so people have also constructed them for tabular problems specifically and for other some other linearly parameterized settings. One nice thing about these algorithms is that they have a bit of a modular structure. So there's a bonus component, there's a policy optimization algorithm component, and maybe in practice you might want to replace NPG with PPO if that works well for your setup. You can even replace linear with neural networks, and maybe you can give out a bonus in terms of the penultimate layer of your neural net. Using that as features. And a lot of these modifications continue to be practically quite effective compared to popular RL methods in hard exploration problems, as we found experimentally. You might wonder, we already had this nice LSVI UCB algorithm for low rank MDPs with known features, so why bother with a new method? And there are, of course, pros and cons in each. So PCPG allows you to handle infinite dimensions, which is not easy for LSVI UCB due to some challenges in concentration of measure. On the other hand, LSVI UCB is much more data efficient. It does very aggressive data reuse collected from past policies and has a significantly better sample complexity. Where PCPG provides the biggest wins are when the MDP you're working with is not exactly low rank in phi. So for what you need for LSVI UCB is the MDP better be approximately low rank in terms of its dynamics and rewards at all states and actions. And in PCPG, what happens is you can relax one of these maxes to an expectation. And we can construct many examples where this is going to be much smaller, and hence PCPG works and LS3I UCB does not. And this, I think, practical robustness of policy optimization methods is one of the most preferable reasons often why we like to use them, both at least in practice. So I want to wrap up and leave you with a few interesting directions for future work. So as we started to understand these optimization-based approaches theoretically, it's natural to ask whether we can bring other traits from the optimization literature, like variance reduction, acceleration, adaptive learning rates, maybe even higher order methods, and so on, to build even more effective optimization algorithms here. All of this relies on this multiplicative weight style updates, which has deep roots, of course, in online learning. And there are many other methods in online learning, which maybe we can use to come up with even better potential functions, better algorithms, for different problem structures. One of the things we talked about in comparing PCPG and LSVI UCB is that PCPG seems much more robust to bad modeling assumptions, but is less effective with data reuse, unlike LSVI UCB. So I think it'd be great to formally understand, first of all, what are the limits to these transfer to the style of model misspecification that these transfer type concepts allow you to handle. And are these truly the extent of situations where policy gradient methods continue to work well, or are there alternative notions of misspecification as well, under which these methods do something sensible? And are there any fundamental trade-offs between robustness and efficiency? For instance, maybe you do more data reuse, you get more data efficiency, but you're more susceptible to model misspecification. Same goes for step sizes in the optimization, right? So understanding these trade-offs, I think, is quite important. And finally, we'll make all these modeling assumptions, and of course, they are bound to fail. And it'd be great to have certain robust fallback guarantees when they don't hold, right? So maybe I'm given some features. If the MDP happens to be low rank in those features, it'd be great to find a near optimal policy globally. If not, maybe I still want to always be competitive with some reference policy without using too much data. How do we design such algorithms? I don't know, but I'm pretty sure it'd be very impactful if we could have such algorithms. So I'm gonna leave you at that. I think John is now going to talk about a very different style of approaches using latent state discovery, but still focusing on computationally efficient methods. And there's bibliography at the end of the tutorial for any of the references we talked about today, if you wanna read more. Thank you.
The fourth part of this talk is about latent state discovery, which I'll go into more detail next. It's time for the last section on the latent state approach. To describe the latent state approach, I want you to think about MDP learning and generalization. So MDP learning lacks generalization. So it's kind of a natural approach to try to add generalization into existing MDP learning approaches. So we know this is possible statistically in many cases, but the goal for this section is doing this efficiently. So can we efficiently use latent state and discover latent state in order to solve reinforcement learning? All right, so the first example here is the block MDP, which actually I talked about previously. How do we use an oracle in order to efficiently solve an MDP? The block MDP problem describes a form of reinforcement learning as we're used to, but there's a little bit of additional structure which is going to make it tractable. We have latent states, we have actions, we have an initial distribution over these latent states, we have a transition matrix, just as for a Markov decision process that we defined previously. And similarly, we have a reward distribution given the states and actions. So that with a horizon defines a typical Markov decision process. The twist is that we're not going to observe the state directly. Instead, there'll be some distribution, Q, which produces our observation given the latent state. Right? So in general, this would be an incredibly hard problem. But we're going to assume that the x's are disjoint over the s. So the observations are disjoint over the states. Any individual observation belongs to some particular state. And that means that there exists some function which, given the observation, can decode the state. We don't know what that function is in advance, but that function exists. And because it exists, this becomes a potentially tractable problem. Okay, so that's kind of the structure that we're going to assume about the world. And then we're also going to assume access to a supervised policy oracle. So we're going to think about a cost-sensitive classification problem where we have a distribution over observations and a cost for every associated action. So this makes it not a reinforcement learning problem because we're going to actually observe all the costs rather than just an individual cost. And we're going to assume we have access to an oracle which finds the policy that minimizes the empirical average cost over a bunch of examples which are given to it. Before I get into the details about what does work, I wanted to discuss several things that have been proposed and which do not work for solving this problem. So one of the common empirical approaches is people use autoencoders. The idea there is that you have your observation space, which is the input, and you map that via some learned function into some small dimensional space. And then you map that via a learned function into a prediction of the original observation space. And the hope there is that by the process of throwing away extraneous information, you get rid of noise and you recover the latent state effectively. Unfortunately, this is not true. It's easy to come up with an example, which is detailed in a paper I'll show you in a moment, where the thing which survives inside of that latent state is actually noise. And so because it throws away the latent state and keeps the noise, this is not a good or effective way to discover latent states in practice. Okay, so that's an approach which does not work. Another interesting approach is this notion of inverse kinematics. So you can try to predict an action given an observation and the next observation. So which action connects the observation to the next observation in a stream of experience. So this is a cool idea, but it turns out this has a weakness, which is requires a little bit of thought. So there's an example here on the right. You have states S1 and S2 that you start in 50-50. Then if you take A1, then S1 goes to S3 and S2 goes to S4. So that seems straightforward. So you can predict that perfectly, right? So you can predict that if you're in S1 or S2 and you observe S3 or S4 next, then action 1 must have been taken. Okay, so then you can do the next one. You can say that, look, if you're in S1 or S2 and S5 or S6 are observed next, then it must have been action 2 which was taken. So far we can perfectly predict the action that was taken, connecting the observation to the next observation. And then if we're in S3 or S4, we end up in S7 or S8, we can predict that action 1 was taken. You can see how this is going because when we're in S5 or S6 and we take action 2, we can predict perfectly that if you're in S5 or S6 and you arrive in S7 or S8, we can predict that action 2 is taken perfectly. Okay, so that seems fantastic. And this suggests that we can consider S1 and S2 to be part of the same latent state. Same with S3 and S4, same with S5 and S6, same with S7 and S8. And that would leave us very happy, except you can observe that it's possible to reach S7 all the time rather than half the time. And so if you are in S1, then you'd like to take A1 and then A1 to reach S7. And if you're in S2 at the beginning, you would like to take A2 and then A2 to arrive in S7. So what this says is that if you treat these pairs of latent states as abstract states, you won't be able to achieve an outcome which is possible to achieve. And yet, this process of trying to predict the action which connects one observation to the next observation does not reveal the information necessary in order to arrive at S7 100% of the time. So that says that we can't use this kind of inverse kinematics in order to effectively discover a latent state for the purpose of exploration and understanding the dynamics of the world. Right, so there's a policy that can reach S7 every time. The last approach, which I think is fairly common, is this notion of bisimulation. The idea there is that you're going to alias states together with the same dynamics and reward processes. It turns out that this is statistically intractable to learn, so we can't hope to succeed with that approach. Okay, so this just tells us there are several approaches which are seemingly natural but suffer from flaws that will prevent us from being able to learn these latent states and thus leverage them in order to discover the dynamics of the world and how to optimize our reward. Let me tell you now an approach that does work. This is the Homer algorithm, which is relatively recently published. The idea here is you have episodes, and in each episode you're going to, let's assume inductively that we have discovered the latent states up to time step h-1. We have, for each latent state, you have a policy which is going to home to that state, so it'll achieve that latent state with high probability. This is where the name Homer comes from. So we're going to use the homing policies to home to the state at time step h-1 that generates an observation x, and then we're going to act according, so that there'll be some latent state which generated that observation x. Then we're going to act randomly, and then we're going to make a next observation x prime. Okay, so we're going to do this several times so we can collect some data. And now there's a new process which is going to occur. We're going to do abstraction. We're going to create a prediction problem. And the claim is this prediction problem is going to effectively create latent states. So this prediction problem is pretty simple. We're going to have x prime triples from the exploration step. For each of these triples, half the time we're going to keep them. So we're going to have xa and x prime, and we're going to just assign them a label of 1. And then half the time we will change the next observation by just swapping in a uniform random x prime and giving it a label of 0. Okay, so now the problem that we're going to create is learning to predict whether x prime was swapped or not. This is done in a slightly complex way because we want to run through a bottleneck. So the function that we're going to learn consists of a phi, which can be very complex. It could be something involving convolutional neural networks with 1 million parameters. And then we have a p, which is relatively simple, it's essentially a lookup table. So the output of the phi is going to be a discrete set of values. So the p is taking as input a discrete set of values for the phi of x, for the action, and for the phi of x prime. And then the p is just taking these discrete values and producing some scalar value, which is the prediction of whether or not the x prime was causal or something from one of these uniform random swaps. Okay, so this is a simple prediction problem. And now for each value of the phi of x prime, you want to try to create a homing policy which maximizes the chance that phi of x prime for the h time step has value s. Right, so that's kind of interesting because we're not thinking of states as given to us, we're thinking of states as being defined by us through this prediction problem. Now we're going to do this at every time step from h equals 1 to big H. And at the end, okay, so there's several ways that we can end this algorithm. One is we can just return the set of homing policies. Another is if there's a reward available, an extrinsic reward available, we can just optimize a policy to maximize the reward that's achievable, and we'll be guaranteed to succeed because the set of homing policies allows us to explore all the dynamics of the latent space. And that means just by gathering data from the set of homing policies, we can effectively learn a policy. And so what can we prove about this? Well, you can prove that for every block MDP, if you can visit the latent states with high probability in your learning oracle's work, with probability 1 minus delta, you can learn an epsilon optimal policy in a polynomial number of samples and compute. Okay, so that's a satisfying guarantee, which suggests that we can effectively add generalization to tabular MDP learning. Okay, so when I describe this to supervised learning people, I often talk about rich observations. So you have some rich observation space, it may be a megapixel camera, you have some deep learning. Given these two in combination, you can learn some covering set of policies, which allows you to home to all of the different latent states. And given the covering set of policies, you can efficiently learn to optimize any particular reward function that you want in the dynamics of that world. So why does Homer work? There's kind of a key observation here, which has to do with this notion of backwards kinematic inseparability. I'll define that in a moment, but if you have backwards kinematic inseparability, it's going to imply that for every pair of policies, the ratio of the probability of observing x prime 1 and x prime 2 is the same. So two observations, x1 prime and x2 prime, are going to be backwards kinematic inseparable if there's sort of no policies which can distinguish x1 prime and x2 prime substantially. In fact, they'll be equal for an exact block MDP. Okay, so this is the implication. This is the important thing to understand about backwards kinematic inseparable. The actual definition is slightly more complex to think about. You say that x1 prime and x2 prime are backwards kinematic inseparable if for every way of producing observations and actions, that's the U, the transition probability to x prime 1 is equal to the transition probability to x prime 2. So this shouldn't be too surprising because a policy provides different approaches to drawing the x and the a. And here we're just saying that for every way of drawing the x and the a, for all of these u's, for all the distributions over observations and actions, the transition probability to the x prime 1 is the same. Homer is just an example of what these latent state approaches might look like. There's several others that we've worked on, and I wanted to give you kind of a step back view and an abstraction in order to think about how these approaches can work. They share sort of three common phases. In phase one, you kind of explore the easily explored things based upon what you know already. And then in phase two, you abstract the latent state space using some form of prediction problem in a learning oracle of one sort or another. While in phase three, you do this covering process. You find how to reach things that were previously hard to reach. So you discover ways to reach things that were discovered through exploration, and then this process repeats. Over and over again, you're going to try to explore the easily explored things, abstract to discover new latent states or new latent state structures, and then you're going to try to cover the new things that you've uncovered through this process of exploration and abstraction. So you can see that very directly in the Homer algorithm. I wanted to give you the flavor of a couple other algorithms that behave in a similar manner. Okay, so let's talk about latent low-rank MDP learning. So actually I discussed this a little bit earlier, but now we're going to discuss an algorithm for learning this in a computationally efficient manner. So just as a reminder, we're thinking about the situation where the transition matrix of a Markov decision process factorizes. And so there's some low rank transition matrix. And now we don't necessarily know what the phi and the mu are here. We just know that they exist. Now, given this, you can create an algorithm. There's one called Flambe which does this, where for each different possible horizon, many times so that you get enough experience to learn, for every covering policy that you've created for the smaller horizons, you're going to roll in with that covering policy for h minus 1 steps. You're going to observe some x. You're going to act randomly for a and then observe x prime. Right? So that's the exploration step. That's very similar to what we saw in Homer, but now the abstraction step is going to be different. We're going to maximize over our choice of phi and mu the log probability of the log predicted probability of the multiplication of these two. So we're learning a phi and a mu, which are different from the abstract unknown phi and mu's which are embedded in the world. And we're learning this in order to maximize the probability of predicting when that x prime follows xa effectively. Right, so this is the exploration in the abstraction steps. And then there's another covering step. And the covering step, essentially what happens is you find policies which maximize the range of the phi of xa. So phi of xa is a vector, and you want to kind of maximize the coverage of its output range. Okay, so this is how we can learn latent low-rank MDPs. And you can prove a theorem, which is similar to the previous theorem, except now we're doing it for a larger space of problems. We're doing it for all latent low-rank MDPs, of which tabular states are one particular instantiation. So in this theorem, you can see there's a dependence on the dimensionality of that rank, and which replaces states as far as the Homer theorem goes. All right, so this is one example, another example of abstraction where you're trying to discover these latent states. It's interesting to notice that we have a different prediction problem that we're solving here. Something which is not just contrastive learning, but rather kind of learning to maximize the probability of something. If you're a physicist, you're used to the idea that much of the world can be approximated as linear dynamics, at least locally. There are many settings where linear dynamics are actually a very reasonable approximation for how things behave. So that makes us wonder if it's possible to actually learn with latent linear dynamics effectively. A canonical example of this is called the cart pole, which is pictured here. And the idea is that you have some pole that you want to have stand up, and you have a cart that you can move back and forth to try to keep it balanced. Here you have this kind of locally linear structure around the solution that you would like to achieve. And now, how do we learn to control the force on the cart back and forth so as to balance the pole? So that's a very canonical reinforcement learning problem. The twist here is that we would like you to do that based upon a camera image rather than based upon the values of f and theta in the picture. So we want to have a latent linear dynamics state, which is very different from what we were talking about previously with a low rank linear transition, so keep that straight, which models the physical world observation that local linear dynamics are a very good way to approximate things. And we want to be able to do this based upon rich observations. So maybe we have a camera which is looking at a cart pole, and based upon that camera view, we would like to be able to control things effectively. Okay, so in order to do this, we'd like to recover the local linear latent state space. And in order to do that, we're first going to try to figure out how to do something with a globally linear latent state space, which is what this is about. So this is a recent paper, which is at NeurIPS. It has a different kind of exploration strategy. For exploration, what we're going to do is essentially act according to a Gaussian for some number of time steps, and make an observation at the end of that episode. And then we're going to try to abstract to get at the latent state space. And the way this works is you build a predictor of the action based upon the last observation for each of the intermediate actions. So that it's a different prediction problem than either of the two that we've seen so far. It's trying to extract whatever information there is in the observation space for the purpose of predicting the sequence of actions that was taken, but that sequence was chosen according to a Gaussian. And then you take these predictions, you create an outer product, and you multiply it with the prediction for an individual observation. And that gives you this f hat. And then based upon this f hat, it becomes possible to do system identification, to recover approximations of the A and the B matrices, which describe the linear dynamics of the system. And then based upon the approximate dynamics of the system, you can start planning to optimize your reward function, which I haven't specified here, but we're assuming that it's some sort of quadratic structure. And then once you start improving this, you're going to need to gather information along the path to the optimal policy so that you can learn to decode the latent structure far from the beginning where you've learned the original latent dynamics. So this process goes on for a while, and eventually you can prove a theorem. The theorem says that if you have rich observation linear dynamics, in your learning oracle's work, you're going to succeed, and you're going to be able to optimize your reward function effectively after a polynomial number of samples and a polynomial amount of computation dependent upon the latent state dimension, not the observations dimension, and the latent and the action dimension, as well as the complexity of the oracle that you're working with. Okay, so this gives us 3 examples of latent space recovery, which seems like enough that we can start hoping to reason about more kinds of latent space recovery. Now I want to leave with a few problems that I think are actually really key problems that we'd like to understand. One of them is, what is the best definition of latent state? People have proposed various kinds of abstractions of state spaces in the past, and what we found is that a lot of them just don't work very well, and it's not at all confident that we have the right one discovered so far. There's several different criteria that we would like to achieve. One of them is it should be tractable to learn. So we'd like the abstraction step in this latent space recovery process to be tractable. That seems like it's a key requirement. You like it to be parsimonious. You want the state abstraction to be as small as possible for the purpose of tractability. And then you would like it to be sufficient. So obviously you could have something which is tractable to learn and parsimonious by just saying, oh, there's only one state. But of course, that isn't good enough. In the real world, you need to actually explore the dynamics in some fashion for some notion of latent state well enough so that you can discover how things work and optimize whatever reward function you care about. Maybe it's getting to the top of the mountain, or maybe it's getting back to your car, or maybe it's finding the restaurant where you want to eat. Something must be done in order to succeed. And so the notion of latent state needs to be expressive enough to allow us to use the dynamics of the world, of the true world, with its true latent state, whatever that might be, in order to achieve a good reward for whatever task we're trying to solve. Okay, so this is a key problem, and I do not know the answer to it. Another key question is, what are other state-making prediction problems? I've actually shown you 3 different state-making prediction problems. And we can see a few things. We can see that the low-rank structure is more general in some sense than just using contrastive learning for discovering discrete latent states. Okay, so that's an observation. We can think about inverse kinematics. If you think about the linear dynamics of the third one that I showed you, is using a form of inverse kinematics. We know that it doesn't work in some cases. It does work in other cases. What's going on here? What is the... Yeah, it seems like there should be some canonical answer for how do you make state from prediction problems. And instead we have several different points showing different ways to make state from prediction problems. Right, so this story is not complete. So this is 2 structural problems. There are other problems that I think are very key. The algorithms that we discussed so far for latent state recovery are relatively theoretical. So obviously you would like to have practical algorithms that can be widely used for solving these problems. And this is a big gap between polynomial, which is what you're really struggling for when you're trying to figure out just the very basics of what's possible, and something which is linear or otherwise highly tractable to use in practice. And so how do we bridge this gap? We need to have more elegant ways to do these things, to discover these latent states and take advantage of them. And so there's a lot to be done in terms of addressing this, in terms of finding the tractable, well-grounded ways to reliably recover these latent states. Okay, so the last problem here is other settings. So I've mentioned several settings. There was the latent tabular markup decision process. There's the low rank latent markup decision process. And there's the linear dynamic setting. There's a lot more to do, right? So maybe you have globally linear dynamics, but you also have boundary conditions, which we didn't deal with. Maybe you have locally linear dynamics. Or maybe more generally, instead of having just a state, you have a combinatorial state, right? So the positions of all of the objects on my desk form a combinatorial state. And if I try to model all those positions as states, then the number of states explodes enormously, right? So our goal is creating a parsimonious explanation, because that's going to be much more tractable to address statistically and hopefully computationally. But we don't really know how to do this very effectively yet. Okay, so I wanted to leave with some final thoughts. First, the biggest thought here is come and play. There are many things to discover, and I would welcome the kinds of insights which I've seen come out of the Fox community in the past. There's lots of empirical and theoretical work going on in reinforcement learning right now. This is a very fertile time for reinforcement learning. And then Alec has been working on a theory-focused book, reinforcement learning theory book with some other folks. There's also a contextual Bandit tutorial if you want to understand that in more depth. This was given at ICML, I think 4 years ago. And then there's the personalizer service, and there's the online learning system, Wabbit, which I mentioned. All of these are available and easy to use or to play with. The last one is that, yes, we are indeed hiring. And so there's a URL there if you're interested. Thank you. I hope this is helpful.